To introduce you to Dr. Tiago de Paulo Oliveira. Dr. Tiago did his undergrad in agricultural engineering in University of São Paulo, Piracicaba, Brazil. Also his master's and PhD in statistics and agricultural experimentation in the same university. And now he has done a range of has held a range of postdoctoral fellowships in NUI Galway, in University of São Paulo. He worked with the Insight Center and Oracle in sports data, and most recently now he is a Marie Curie Fellow in the University of Edinburgh, working at the Rosling Institute. So please, Tiago, the floor is yours. You're very welcome, and thank you very much.
Thank you, Rafael. Thank you so much. This is a work I did with Rafael some months ago. It's about a hierarchical state space model, and we use this kind of model, including a autoregressive component and some parameters to capture dispersion. And we apply this model to get some idea about short-term forecast of COVID-19 cases worldwide. And I divided this presentation into 6 sections. It's the standard one. I will talk a brief about the introduction, motivation, data acquisition, how we developed our methodology, and some results discussion, final remarks. And in the end of my presentation, I will show the Shiny app that we still are, it's under development. We are still implementing some stuff, but I think we will finalize this up to next month. The COVID-19, it's, as you know, is a new disease, and there are a lot of factors acting together. And generally, we don't have access to this kind of information. And in our model, we are just accounting for country, basically. But we know that the virus is spread with great speed. There are some relationship, for example, human behavior and government intervention and policies, and this should be specific to state to state, from city to city, and this is a very challenging kind of modeling. And the other thing is that the data quality is generally poor. Generally the number of reported cases that doesn't reflect the reality. And in this situation, if we can get a great accuracy forecast, this kind of model, it's proved itself invaluable. Here I'm showing two countries, like here's China and Russia. That's just show that we can get some idea about the trend using this kind of short-term forecast. For example, in this, here's just July, but in China, we expect like exponential increasement in the reported number of cases, while in Russia, we expect a linear decreasement. When we get knowledge about the trend, we can do like crucial assisted planning, and this kind of forecast is also very useful for cities, low, middle income countries, and they can get from this forecast some strategic planning to avoid overcrowding or reduce the number of deaths over time. Well, here I'm also showing 6 countries, Bolivia, Ireland, and Israel in the right side, in the left side. And just to show that we expected it in the next week, almost the same number of cases in Ireland, and the same thing in Bolivia, while in Israel, we expect a little bit increasement in the number of cases. And it's completely different when compared with Germany, Russia, and the United Kingdom. Here we are expecting for the next week a linear increasement in the number of cases. Well, using this idea about develop a model to get a high accurately forecast, we use this approach, a state space hierarchical model. And from this model, we generate forecasts up to 7 days. And we get information from the autoregressive part of this model to clusters the countries based on their behaviors in the last 60 days. And we also provided this, everything, all our results is provided as a Shine dashboard, including the model validation. And we provide the point forecast, the prediction intervals, and everything we did is free and available online in my GitHub. The code, data, just the Shiny app is not available, the code of the Shiny app, but the other thing is everything available here. The data, we are still using the European Center for Disease and Prevention Control, ECDC. And generally, when we downloaded this data, and if we don't have all the countries, sometimes we have a problem because if we download it, for example, the data at morning, we don't have access to the number of cases for all the countries. And then we just remove the actual day, and then we forecast the actual day plus 6 days. And if we have all of these countries there, we will forecast tomorrow and plus 6 days. This is the data structure that we have now. Is the time, number of cases, number of deaths, countries, the population associated to country, and the continent. To illustrate our idea, we are just using, in this case, time, number of cases, and countries. But this model is still possible to extend it to number of deaths and number of hospitalization, and so on. Now we have around 46,000 observations and 210 countries. Well, about the methodology, we are assuming that our actual reported number of cases, given the past reported number of cases, follows a negative binomial distribution with this expected value and one parameter, the natural parameter of overdispersion. The thing with this assumption, we try to assume that this relationship follows a Poisson distribution, and including, I will talk a little about it after, but including this is another component that allow us to get some extra variability in the model. We tried the Poisson, but the Poisson is not doing better than the negative binomial. And then we needed 2 parameters of overdispersion here. The first one is the natural parameter of the negative binomial. And then in the linear predictor, we are using the canonical one. And this is equivalent to, it's a function of 2 components. The first one is the autoregressive component, the gamma. And this one is allow us to get extra variability in the model. Well, the difference here, the different way about how we are modeling this autoregressive process is how we are fitting this coefficient of the autoregressive process. Here we are assuming AR1, autoregressive of order 1, with white noise follows the standard normal and with this variance component. And the way we are fitting this phi, it's depending on the country and depending on time point. And to handle with this with a lower number of parameters, we assume this is a it's like a regression. We're using the time as explanatory variable. Well, to get a specific autocorrelation function per country, we use this random effect of country here and then we can include a specific random effect in each of these fixed effect parameter, like intercept and slope and so on. And then we assume this random effect has a multivariate normal distribution, assuming initially a unstructured structure. Well, and then we included this other component to explain the extra variability in the data. Basically, this component depends on two other ones. The first, lambda, we assume a Bernoulli distribution with parameter p, and then when lambda is equal 1, this means that our model needs this extra component and need this extra component, and this component follows a normal distribution with this variance component sigma square omega. This means that when we have some kind of outlier in our data, we will probably need this extra component in our model. If not, otherwise, this lambda will be 0, and our model will depend on the autoregressive process here. We can try to iterating this autoregressive process and get this equation 1. Basically, the actual gamma component will depend on the first one for this specific country, and this will multiply by the productory of this fifth, the AR coefficient, plus all the noises without the actual noise, multiplied by the productory of this coefficient as well, and then plus this white noise. The thing here is that we can show, if we assume, for example, that each country has a specific autoregressive process of order 1, we need just the intercept and the random effect in the intercept, and then we get this autoregressive process specific for country. And if we assume that all countries has the same coefficient, we just drop out this random effect, and then we come back to the AR1, the standard AR1 function. To work with this kind of forecast, we try the mean and the median, but the median is far better than mean in terms of accuracy between the observed value and the forecast value and the true value. And it is also reasonable to use the median because we have we accumulate the error terms from one time to another. And you will see in our Shiny app that the forecast interval is it's high asymmetric, and then we are using 7 days, as I said. We use the Bayesian framework to handle with the parameters, and we assumed the prior for the variance component is a gamma one. For the fixed effects parameters, we assumed a multivariate normal distribution. And for the P associated with the Bernoulli, a uniform 0, 1. We use 3 Monte Carlos MCMC chain and 2,000 adaptation, 50,000 S-Burn-in, and plus 50,000 interactions, but using 25 as thinning to try to reduce the autocorrelation in the chain. Well, how we validate our model? Basically, we divided our data set in testing and training. We leave the last 7 days as test, and then the remaining data is used as training set. And then to compare the forecast with the true value associated with each country, we we used the concordance correlation coefficient proposed by Lin in 1989. Basically, this concordance depends on covariance components, variances, and expected values. You can assume, for example, sigma square 1 is relative to the true value, while sigma square 2 is relative to the forecast, and then we get the covariance between them, the expected value for each one, and then we can rewrite this equation as we can rewrite and we can prove that this is equal two components. The first component, rho, is the Pearson correlation coefficient that is associated with precision, while CB is the bias corrector factor associated with accuracy measure. Everything about this concordance is quite very well explained by Lin in his paper. Well, what we did, we are calculating this concordance correlation coefficient for each time independently, and then we get the concordance for each of our forecast days. We also worked with clustering, and basically we get the estimates of our autoregressive component, and then we work with this component to get some idea about similar behavior of each country related to the last 60 values of this estimate, the last 60 days, basically. However, in this case, we are very interested in the shape of the temporal series between countries, and then we use the dynamic time warp proposed by Miller 2007, and basically we have, for example, here R is the pair of estimates of our component gamma for different countries from time 1 to time m. But we can rewrite this R in any ways, because we can get, for example, gamma I1, gamma I comma 1, gamma I1, gamma I2, and gamma I comma 1 again. And then we can reorder this R, but always preserving the observation order of the initial R. And then we can solve this equation, minimizing this sum of the difference of absolute values of these gamma components. We can see this in a better way, seeing these plots. Basically, imagine we have this country Q and this country C, and if we use the Euclidean distance, we have here a linear alignment between the points of this time series, and the Euclidean distance is a particular case of DTW. And when we use this DTW approach, we are looking for a nonlinear alignment. This means we would like to know if the shape of this red temporal series is close to the shape of this blue series, without care about scale or shift. Basically, we need at the beginning to identify all the peaks, and then when we identify these peaks, we try to mapping from the left and right side of this peak, left and right of this, and so on, and then we get a mapping like this for. But remember, we have 210 countries, and we need to do the problem is, as we have a lot of possibilities of this is very time consuming. After we get to this DTW, we use the WARD method and to get the hierarchical cluster, and then produce a dendrogram using this hierarchical cluster analysis. I will show this result particularly in the Shiny app because it's easy to see. Well, here I will show you some predictive performance of our model. We did three prediction performance. This is the first one from 3rd April to 6 May, the 7 days. In the y-axis, I have the forecast, the logarithm of the forecast, and in the y-axis, I have the true value observed in each country. And then you can see that from 1 day ahead to 3-4 days ahead, our forecast it's very good, and you can see the concordance correlation coefficient is still high. It's around 0.8 here, and then the day 5 this drops to 0.75, but the accuracy is still high. And then from day 6 and 7, this dropped a lot. Well, this means that we can believe in our forecast up to 3-4 days, and we can use 5, 6, and 7 with carry. We need to take care about this. But generally, the forecast, the estimative of the forecast for from day 4 to day 7 is every time higher. The report number of cases higher than the true value. And well, this is better than the opposite, in my guess. The same type of performance we got from the second time. This is from 7 May to 13 May. And we have a very good forecast up to day 4. And then this starts to be positive bias from day 5 to day 7. The concordance precision and accuracy is still high up to day 4, and then start to come down after day 5. And the same result here, but the accuracy is still high for all of these 7 days. This means that the points is around this equality line. The autoregressive component, it's a particular useful function because there's a straightforward relationship with the pandemic behavior. If you see here Brazil, for example, Brazil has a very strong seasonality, and the way we are modeling the parameter phi is allow us to get this seasonality quite well. And then you can see this the seasonality generally on Monday, Tuesday, the report number of cases go down, and Wednesday and Thursday this go up again, and we have this cycle that the seasonality is very strong in Brazil. And we also can see the pandemic waves, or when the virus starts to increase again. For example, in China, we have this first wave, and then the virus starts to increase again in the between 20 March and 20 May, and then they control it and start to decrease, but after July, they lose control, and then the virus starts to increase again. In Ireland, we are in the second wave. Basically, we had this first wave that, in the second wave started close to 20 July. The same thing in United Kingdom. We are, well, Ireland at least control better than United Kingdom, and we are now increasing again. This is other result about the extra component to control the variability, and then basically when lambda is equal 1, we need this extra component and allows the model to get this extra variability. These colors represent when lambda is the probability of lambda be equal 1, and then when you see blue points, this means that we need this extra component. And this result makes sense. For example, in China, we have this outlier here. A lot of people, they report a lot of people with COVID-19, and then we need this extra component. In this case, we can see, for example, here in Iceland, but in the other direction, we have here in France two points that we needed this extra component. In Spain, the same thing. And sometimes this component appears, for example, here, when there is a few number of cases. Well, we need a further research between the confounding of this omega with the natural parameter of overdispersion of the negative binomial distribution. Here's some the estimates. This estimates is, I think, is from May. I don't remember, but I think it's from May. And this shows that just to remember you, the phi is modeled depends on these betas and these variancy components. These 6 parameters here is just to model the phi parameter. And then beta zero represents that our autoregressive processes starts almost as a random walk, and then the phi starts to be to decrease, and in some point they start to increase again. Clearly, this is the mean value of the phi, but when we added this, when we see the profile, the phi profile for each country, this could be just decreasing or decreasing and increasing. This will vary because these parameters is the estimate of the standard deviation is very high, and then this beta 2 could be just negative and this negative, and then the phi just will decrease. The p value represents that in mean we have 11% of the number of cases can be viewed as outlier. It's a huge number of points, and then this can vary from almost 10% to 12% of the data points, and this is the estimates for the extra variability, and this is the estimate from the extra variability, the overdispersion of the negative binomial. It's really different. Well, some final remarks about our approach. We established this novelty in terms of modeling the autoregressive parameter, and we can translate directly into improved predictive power in terms of forecasting future numbers of daily case. Clearly, we can extend this model for different areas. And I think this model will be better if, for example, imagine we have in Ireland or Brazil or United Kingdom, we can include a more complex hierarchical structure in this model, and we can see what's happening in each city within, for example, city within state within country, and then we can forecast the number of reported cases, number of deaths, number of hospitalization for each city in a specific country, for example. But we don't have this information now. There's some problems. For example, if you go to United States, Brazil, China, generally it's difficult to forecast there because in terms of country, because there's a lot of aggregate heterogeneous subepidemics in different local areas. For this kind of country, it's much better we look in terms of states or regions within the country. And this is also very important because we are working with with a different data from different countries, and then our forecast is just a direct reflection of the data collection process, be it appropriate or not. Here's some references, and I will show you now the Shine app. Cool. Are you seeing my screen, Rafael?
Yeah, it's perfect. Yeah.
Great. Guys, if you have any question, please, we can discuss about questions while I will present the Shine as well. Just you can, I mean, I don't know, Rafa, if you allow people to speak or they will write in the.
So there's a raise hand feature that they can use there. But at the same time, if they write anything in the chat, I'll read it to you later on.
Brilliant.
Okay.
Well, this is the look of our Shine app. We have here the interval forecast, and here's the observed points. It's not the estimate; it's just the observed points. But here's our forecast for, in this example, for Ireland, and we expected for this week and next one almost the same number of cases, and this will not show this will not reduce over this week and next week. And the problem, as I told you, you can see that very asymmetric confidence interval, credible interval for the forecast. And this starts to be not so trustable in for example, day 4, 5, 6, and 7. But we can use it, this confidence in the first days, first, second, and at least in the day after 3 days as well. But again, we are using 80%. If you go to 95%, this will be far more problematic. And clearly, we need to get some further improvement in the model and look what's happening with this kind of asymmetry. It's just the variability of the data, or we can include some more component to forecast odd counters. I really don't know. It's something that we need to study more. Here we are showing some forecasts for tomorrow. For example, Ireland 236 and United Kingdom 22,000 and so on. You can include some other countries here. For example, I can include Brazil or Portugal. And then we can handle with this to be a little better to see what's happening. Oh, no, not too much. Yeah. And again, this seems that this is not varying, but this is because the size of this credible interval. If you go, for example, to the point estimates, and then you can see what's happening. For example, here in the United States, we expected an increasement over time in the United States, while in Brazil will be the same, around the 11,000 of new reported cases. We can see here, for example, Ireland. And then, as I showed in my presentation, we expected almost the same number of cases in Ireland as well. We can go to another countries, for example, Spain, France. This depends on the number of cases. Yeah, I think this one. Yeah, we can looking for different countries to see what will happen in each of them. We can see all the series here, or just focusing in the forecast. We can also see this one as in the log scale or not. The same thing in the interval, we can see in the log scale as well or not. We have a summary here, and then you can see the numbers just for Brazil, and then we have the daily numbers here, number of cases, and the confidence of the 3 confidence credible interval as well. Another interesting thing is this autoregressive component, and then we can see, for example, in China, what's happening over time. But let me see different countries. Here an example of 4 countries. Cool. And basically, Europe is in the second wave, and the second wave, for example, in France is started here around 9 of August, 9 of July, and here it's in Portugal. This started around 15 August, Italy 7 July, and Spain probably 7 July. I mean, you can get some information using this autoregressive component, and you can see how your country is doing over time. And the last thing I show you is the dendrogram. I generally use the fun because you can see all the countries together. Just increase a little bit the size. Okay. Yeah, here we can see better. Well, for example, in this case, we have 10 clusters, and this is, we can see that Brazil, United Kingdom, Russia, Colombia, France, and Spain is in the same group in terms of behavior in the last 60 days. And Ireland is close to Puerto Rico, Honduras, Panama, Kuwait, and so on. Well, we can use this to see how is the policies of these countries related to Ireland. And clearly, we can also use, because here we are using the number of reported cases, but we can also extend this to the number of reported cases per million or per 100,000 people, and this plot will change. I think it's everything. The model validation, we have these plots as well. For example, if I'm looking for Ireland, Brazil, I think here it's UK, yeah, UK, Spain, and so on. And then we can see how the model is doing these 3 validations we did. It's doing quite well for most of the countries. And here, these points, these countries is very complicated because sometimes they are reporting 0 cases, 1, 2, 3, and then they start to report 1,000 cases, and then go back to 1, 2, 3, and it's really difficult to get a good forecast for these countries here. And as you can see, as I show in the presentation, this starts to be positive biased. Yeah, and this is the 3 plot I showed about the concordance correlation. Yeah, I think it's everything. If you would like to open, Rafael, to questions or.
Yeah, okay. Thank you very much, Thiago. That was very good. Thank you.